Hello, everyone. I am very excited to introduce and promote this senior design project to all of you today. This project is called Accessible VR Protein Space with LLM and Voice Interaction, or PLM verse 3. As the name suggests, this is already the third generation of our system. The previous two generations built a solid VR platform, and now we are ready to take the next step. Although you see the words protein space in the title, don't worry too much about the biology. Our focus is really computer science and technology. Protein space is simply one application of our VR platform. Our goal is to innovate VR technology and make it much more accessible. Thanks to today's advances in large language models and voice recognition, I believe accessible VR is no longer a dream. It is something we can realistically build today. Before introducing the project, let me briefly introduce our research lab. Our lab, Integrated Digital Omics Lab, is in the School of Computing at the University of Nebraska-Lincoln. Our research focuses on computational science for biology. In other words, we use computer science techniques, algorithms, artificial intelligence, databases, visualization, and software engineering to solve biological problems. This project is a perfect example of combining modern computer science technologies with real scientific applications. Now let me introduce protein space. Simply speaking, protein space is the idea of putting all proteins into one common space, or even one huge universe. A protein is a biological molecule, but for us as computer scientists, we don't need to think about all of its biochemical details. Instead, we simply view every protein as a sequence of letters, a string. Just like a sentence is made of words and characters, every protein can also be viewed as a sequence or a sentence. Once proteins become sequences, many computer science techniques become applicable, especially machine learning and language models. Just like sentences have similarities, protein sequences also have similarities. Some proteins are very similar to one another, while others are quite different. Modern protein language models can measure these similarities and project millions of proteins into a single space. As a result, similar proteins naturally form clusters or neighborhoods. In this example, protein 1, 2, 3 form a cluster, and protein 4, 5, 6 form another cluster. From their sequence-level information, you can tell their similarities. So when they are put into a protein space, protein 1, 2, 3 become neighbors, and protein 4, 5, 6 form another neighborhood. This kind of visualization is extremely valuable for biologists because it helps them quickly discover relationships that are difficult to see by looking at sequences one at a time. Once proteins are organized into this space, users can start exploring. For example, a biologist can select a protein and examine its sequence in detail. They can also select a neighborhood to find similar proteins and compare common sequence patterns. Our current system already supports single selection and multi-selection, allowing users to interactively explore protein space. There are many more interesting functions that we can develop in the future, and that is exactly where this senior design project comes in. This idea is not just ours. Companies like Meta, formerly Facebook, have already built enormous protein spaces containing hundreds of millions of proteins. If you're interested, you should definitely check out their online visualization. It is very impressive. However, their visualization is still mainly viewed on a traditional computer screen. Our goal is different. We want to bring protein space into a fully immersive 3D virtual reality environment, making exploration much more intuitive, interactive, and, honestly, much more fun. This is the first generation of our platform. Thanks to the previous senior design team, we already implemented both the desktop version and the VR version. Both are using web technologies. More importantly, our system is compatible with different VR headsets, while also supporting users who do not have VR equipment. In other words, our platform is already accessible from multiple devices, giving us a solid foundation for future development. The second generation added another exciting feature. Besides the personal mode, the team also implemented Leaders Mode. Personal mode is designed for an individual user exploring protein space independently. Leaders Mode is designed for teaching and collaboration. A teacher or team leader can guide everyone through the same virtual environment, allowing students to follow demonstrations together. This opens many possibilities for education, presentations, and collaborative exploration inside VR. So what should our third generation focus on? Our goal is to make VR much more accessible. Instead of relying entirely on controllers and complicated menus, we want users to interact naturally using their voice. The idea is to combine modern speech recognition with large language models. The system listens to a user's voice, converts speech into text, understands the user's intention, and finally translates that intention into VR operations and commands. Imagine simply saying, "Search similar proteins," or "Move to this neighborhood," instead of navigating multiple menus. Of course, before building new features, the first step is to become familiar with the existing system. Play with the current platform. Understand how it works. Identify the important functions and think about which operations could benefit most from voice interaction. As a senior design project, we don't need to implement every possible feature. Instead, we can focus on a few important tasks, such as search, navigation, selection, or interaction, and redesign them in a smarter and more accessible way. Here is a simplified system diagram. Our existing VR platform already provides a solid front and back end for visualization and interaction and searching. What PLM Verse 3 needs is a new or another back-end engine that connects speech recognition, large language models, and command interpretation. This new intelligent engine will become the core technology that powers accessible VR and enables natural interaction between users and the virtual environment.
Students, you will definitely impact the visualization world with VR and AI. In the short term, we will make VR systems much easier and more natural to use. In the long term, we hope to contribute to the future of immersive scientific visualization. Although today's application is protein space, the technologies we develop, voice interaction, LLM integration, and accessible VR, can eventually have broad future potential. I hope this project has sparked your interest. If you're excited about artificial intelligence, virtual reality, software engineering, human-computer interaction, or building real research software, I think you'll find this project both challenging and rewarding. We already have a strong foundation. Now we're looking for a great team to build the next generation together. I would be very excited to have you on board, and I hope you'll join us in making PLM Verse 3 a reality. Thank you.